Okay. Mic test. Work? No? Yes? Yes. Okay. Thanks. Questions? Thanks. I don't know if TA sent like email or something about the doodle, like scheduling. No, not yet. Probably you will receive email or request from TA regarding basically to figure out whether there will be semi-regular time that we all can meet, right, to make up lectures. Okay? So if you receive it, please respond soon so that we can figure out make up schedules as soon as possible. We don't have much left, right? Basically month and a half. Crazy. Month and a half. And yet I counted as we need about 6 lectures, so 3 weeks worth of lectures, which means this is the first week of November, second week of November. First week. So, which means that we want to start having a method of lectures already, right? Hopefully at least once per week, or if possible, twice. Okay, any questions so far? Okay, if not, we will continue developing S-metrics and then scattering amplitude. And last time, we talked about the definition of a scattering amplitude in terms of asymptotic state, right? And then we define S operator. So let me quickly remind you, and then we will continue the construction. So scattering amplitude. So we defined it as an overlap between asymptotic in state and asymptotic out state, which is time independent because they are basically 2 different bases for the same interacting Hilbert space. So they will evolve according to the same Schrödinger picture evolution operator. And then using a definition of an in and out state, which is basically asymptotically looks like free state, right? So we were able to re-express this in terms of this is a free state, and then there's an S operator, and then again in free state, and S operator we found out that is basically same as interaction picture time evolution operator from minus infinity time to plus infinity, which we can write it as time ordered exponential of minus I minus infinity to infinity, and then interaction Hamiltonian, but in interaction picture. Or we can introduce Hamiltonian density, so we just rewrite it as integral over d for x, so this looks like a more manifestly for x invariant, and local, so we can write this. So that's what we established last time. Okay, so today I will basically start talking about how to think about this object. Okay, so this is a formal expression. And then we will discuss extending this object order by order in perturbation theory. And then we will also discuss how we can express this somewhat, complicated looking string of operators in terms of diagrams, known as a Wick diagram. And then we will later talk about the Feynman diagrams. So these are slightly different, closely related, or slightly different. And we will talk about it. So let's first just talk about it. Now, one thing to talk about here is that this is time ordered, and the time ordered operator, string of operator makes sense if you have an expression, a string of operator which carries time labeling, obviously, right? Without a time labeling, we cannot do it. So the first thing I want to talk about is that we can rewrite this expression in terms of some other form according to what is known as the Wicks theorem. Okay, so basically, I will establish the following thing. So eventually we want to establish the following expression, formal expression. So whenever I write this in the subscript, I really mean phi operator is inserted at x1, including time obviously, and then phi xn. So I'm just gonna write this simplified version, okay? Just to save some time. And then eventually we want to understand the following formal expression. There's n. So a lot going on here. So at least you have seen this, which I will remind you again today. So this notation is for normal ordering. And then you also see some weird notation. Nice. So no blue chalk today. You are forbidden. So we're going to use red today. So this notation is what's known as contraction, which we will also talk about. So the statement of the Wick's theorem is that we can rewrite time-ordered string of operators in terms of normal ordering and then contractions. Okay. Now, before I start, let me quickly remind you normal ordering, and then I will define the contraction. Okay. So what was normal ordering? This is just a reminder. So normal ordering is defined for, this is defined for a free field. Why is that? If you recall, the definition just says that if you had a free field phi of x, then we went u, which can be written as alpha e to the minus, and then beta dagger if it is complex field, to be just more general. So I'm suppressing just the measure, just to simplify the expression. Normal ordering, if you had a chain of operators, phi 1, phi 2, whatever. So when you put normal ordering, that means that annihilation operators go to the right, and then creation operators come to the left, right? So that's the normal ordering. So very definition, therefore, normal ordering is built in based on the notion of free field, which has creation and annihilation operators. Okay? Good. So that was normal ordering. Let me define the contraction, and then we will start showing this expression, gigantic expression. So definition of contraction. So let's consider two operators, A of x and then B of y. And I'm assuming these are free fields. Okay? Because I have to talk about normal ordering. So assuming these are free fields. So contraction, I'm going to write it as this is defined to be a difference between time ordering of the two minus normal ordering. Okay, so that's the definition. Okay, so now let's actually work on and see how it looks like. So suppose, consider first, x0 is larger than y0. So what I'm going to do is that we want us to look at how this actually look like. Okay? That's two formal expressions. So we want to actually look at how it looks like. So then time ordering is basically clear. So this is nothing but just A of x, B of y for this particular time ordering, which I picked. Let's actually now look at this. So what is this? So time ordering is left hand side is given by this. I'm just writing this. And we talked about the fact that in a maximally confusing way, so let me just suppress, we can divide free field in terms of this plus part, which has a annihilation operator with either the minus IPX, right? So completely opposite. Okay, and then I can do the same. So plus. Okay, so that's done. And let's expand. So it's an obvious thing. So let me just suppress notations like this. Okay, so D plus Y. Okay. Let me see if I can do this well. So far, so good. think this is trivial, right? Okay, successfully done. I just literally wrote it. Now, using red chalk, let's just check which one is already normal ordered. Yes?
What are the plus minus?
Oh, so if you recall, free field can be decomposed into plus part, which includes the annihilation operator, then part that has creation operator. Okay? Everything is backward. I mean, it's actually lucky that everything is completely backward. What if this is plus and this is minus? You're screwed, right? There's no way to remember this. Anyways, it's completely backward. Now let's check which one is already normal order, right? So this is normal order already, right? This is alpha to the left, alpha to the right. Both are annihilation operators. So this is normal order. Both are creation operators. This is normal order. Annihilation to the right. This is good. So this is normal order. This is not normal order, right? Creation to the right, annihilation to the left. So this is not normal order. But I can insist on writing normal ordering according to as follows. So instead, let's add a normal order to this. B minus y, a plus, but obviously I have to subtract because there's no free lunch. So now that is completely normal ordered. Are you with me? But I have to have it. So therefore, time ordering, which is what I was writing, is the same as normal ordering, and then there's this commutator. Boom, this with that. So ax plus y minus. Okay, so honest, straightforward algebra. So what we learn is therefore is the following: a contraction of two operators, which are differences, of time ordering and normal ordering, is given by when I assume x0 is greater than y0, it was given by a of x plus b of y minus. Okay? And you can do exercise exactly the same. Basically, you just change the role of a and b completely, right? So then you should get by plus ax minus. So that's the more explicit expression for contraction. Now, you may recall the following. So this object, a plus x b minus y, is given by, so if a or b are same operator, basically phi, right? And then in that case, basically you're looking at the commutator of these two with the same alpha here. Okay? Then alpha commutator with alpha dagger is basically delta. They contract, you basically have the product of these two with a measure. So that we gave a name, which was delta sub minus x minus y. And more explicit expression is ep to the minus ip x minus y. So that was this function, and we talked about this a lot in the context of causality and whatnot. Okay? So first of all, this was a Lorentz invariant function of x and y. We used the fact that in space-like separation, you can put this Lorentz, so we use all kinds of stuff. In particular, you see that this contraction, which is basically the delta function times this commutator, you might say, oh, that's commutators operators, but these are manifestly C number. Right? This is just an integral function. Obviously, if A and B are not the same, they're just zero. Because if you look at the commutator between the one kind types of creation or annihilation operator and with the other, obviously it's zero. So good. So therefore, if we just look at the same contraction of the same operator, let's take an example of real scalar field, and that does delta plus x minus y. And you can try to combine this expression slightly better. You probably have done it in one of the homework problems presented in the Coleman's book, that we can show to be P4 P, then P squared minus M squared if it is a massive particle, then e to the I x minus y, where you have to take the limit epsilon goes to 0 from positive side. Okay? So depending on whether this is positive or not, you can choose a contour, and then you see that the appearance of theta function. Okay, so that's what we have seen. What is new here is that we just discovered the fact that if I define the contraction in this way, as a difference between the two, it is basically nothing but in the case of a real scalar field, which will be also true for complex, this is a propagator. Okay? Now, it's completely obvious, but there's another useful thing to say about this. Let me just say it. So another useful representation of contraction is the following. So let's still pretend to be some general. What we have just seen is that this is just a C number, not an operator, but C number. Okay, and in particular, this is nothing but represent the propagator. Okay, since this is a C number, it should be same as putting it inside of vacuum expectation value. So the first equality should be obvious. It's a C number. Now let's use the definition. So this is time ordering of A minus normal ordering of A and B. But the construction of a normal ordering is precisely such that when you look at the vacuum expectation of a normal ordering, it's trivially 0. What it means is the contraction is nothing but vacuum expectation value of time ordered 2-point function. Okay? Otherwise known as a propagator, which already confirmed is a propagator. Yes, that's what I used. This is true whenever this is a free field, as we just proved.
Yeah, so provided that we know that we can write that equally, right?
This equal, right?
Yeah. It is not a different offers.
I just said there is just a rephrasing of the same thing, but it is good to see explicitly. It's not a different thing. I'm just reminding you from the definition. It is also good to see explicitly that the contraction is equal to nothing but 2-point function. Another question. Good. So that's contraction. Now let's build. So let's consider now contraction, slightly more general case. So suppose I had a time ordering of actually let's look at the normal ordering of A and A, B, C, D. And then I don't know if you have a contraction of these two. Okay? This part is just a C number. So which means you can take out of normal ordering expression. And so basically this should be the same. No. Same as this, for instance. So hopefully now you understand. You will see again and again and again. By 2, by 3, by 4, by n minus 1, by n. There's this big normal ordering symbol out. But hopefully it's clear that even if you see this type of expression, you know what I'm talking about, right? There's a string of operators, and then whenever there's a contraction, this is represented by basically propagator. If you like, you can take it out of the normal ordering system. Okay? There's no difference. Good. So now let's actually look at the Wicks theorem. Okay, so to show Wick's theorem, so let me phrase the Wicks theorem a slightly different way. Instead of this somewhat formal looking expression, Wicks theorem basically states the following. Time ordering of n string of n operator. So for now, let me just take it to be real scalar, but it doesn't matter eventually. And Wicks theorem says that this is equal to normal ordering of entire n field without any contraction. And then normal ordering with the one contraction, but including all other possible one contractions. And then all possible two contractions until you saturate. So basically, this is the last thing just represents either n over 2 if n is even, or n minus 1 over 2 if n is odd contraction, which is unique. Well, if it is odd, obviously there's an n different kind of thing. You have to take it out, and then. But if it is even number, you will use a single term. Not a single term. So there's all combinations of, I'm saying, n contractions, n over 2 contractions. You know what I'm saying? So the statement of Wick's theorem is that time ordered string of n operators can be represented as basically normal ordering with the 1, 2, 0, 1, 2, up to maximal possible contractions with all possible combinations. Now, what's remarkable about this statement is that this is true with everything in front of just plus 1 here. So every combination, every possibility appears with the same weight, okay? That's the important piece of information. Now, I'm gonna show this. At least I'm just gonna demonstrate why this might be true. And we will use this now to talk about the Wicks expansion and Wicks diagram. So here's a sketch of a proof. And we'll prove it by mathematical induction. Right? So whenever you have to show something in general with the arbitrary n number of things, that's how things go. So the first step, P over phi 1 is that. So let me use the notation that the entire right hand side. Okay, the entire right-hand side of the Wicks theorem, I'm gonna use it the same symbol as what Coleman uses. So I'm just gonna call everything on the right-hand side of the Wicks theorem to be Wick or W phi 1 to phi n. Okay, so this is normal ordering of a 0 to n whatever maximum contraction. That's the symbol. So you see, this is trivially true. First of all, this is normal order, right? By definition. And there's no contraction to talk about. But that's not quite fair, the initial point. So we already there was a definition that this is equal to phi 1, phi 2, which is basically the same as this normal ordering without a contraction plus phi 1, phi 2 contraction, because that was the definition of this. Okay? So the initial point is done. Then we will assume that this is true for starting from 2. So this is n minus 1 of them is equal to W of phi 2 to phi n. We will assume. Then we want to show, as a mathematical induction work, this is true for n chains, right? So that's what we want to do. So to just do this, So I'm gonna do without loss of generality. I will assume just consider the fact that there's a. I'm gonna take this particular ordering of the time. Okay. So for any given string of n operators, if you know the ordering of the time, I can always just relabel the operators according to 1, 2, 3, 4 in a way that time increases or decreases towards the end. Okay, so which I can always do. So and hopefully you see now why I use it from 2 to n, because I'm about to add the last one, which I assume to have to be the latest operator. So I can multiply this thing. Just write this by 1. Which is equal to, according to this assumption, pi 1. Okay, done. And this is, by construction, is time ordering of entire n operators. So I just need to work out the right hand side. Which we can do. Let's do it. So far, so good? Okay. So let's work on the right-hand side. So phi 1 of the plus part, which is annihilation, and the minus part, creation part, w by 2 to phi n. And this can be written as follows. Phi 1 of minus first, and then I insist on putting this after that because I like to have a long ordering, but then I have to compensate by phi 1 plus w 2 n. Okay. So are you okay with this equality? Now, what we have to convince ourselves is that this, so we want to see, basically, right? This is equal to W1 to n. So let's see why that's the case. Okay? So what do you expect if this were to be the same as W over phi 1 to phi n? Well, you want to see from here that, well, it has the entire sum of normal ordering. So the entire thing is normal ordered. 0, 1, 2, to maximal contractions. That's what you want to see. Now, what is this W object? This is completely normal ordered, including 0 to maximal contractions among the 2 to n. Now, this object represents, this is normal ordered, right? And this is normal ordered. So this first line basically contains everything which is normal ordered, as you'd expect, including all possible contractions without phi 1. Completely normal ordered, every possible contraction, but without a phi 1. So this first line, what it misses is that every normal ordered piece with phi involving in the contractions. That's what this thing is missing. What was this commutator do? So it picks up whichever one is not contracted yet. Right? You will pick one by one and get it contracted. So this thing is again normal ordered. Why you might say, oh, why? Because this is appearing on the left hand side. But the only way phi 1 involves is when it gets contracted. Right? Whenever phi involves in the string with only normal ordering without getting contracted, this is already contained here. So every normal ordering with the contraction without phi 1, and this is every normal order, not including phi 1 contractions, with exactly coefficient to 1 and 2. Okay? And that's exactly the definition of W. Hence, the theorem. Okay, good. Now, I want to just rewrite this in a fancy way. So let's write that in a fancy way. Okay, so that's slightly not sufficient. Okay, so let me just rewrite this part. So therefore, Wick's theorem can be restated as follows. So that is equal to, something fancy. So then here, right? Is equal to, what do you want? Well, conceptually what do you do is that you want to have a always normal order, right? So everything is always normal order, right? And then you just want to pick two guys. The first time, no. Second time, any two guys, and then put them on contraction. Second time, you pick any two pair, and then put them on contraction, etc., etc. So then that can be done as follows. That was what I was writing at the beginning. Which one is easier to write? This or that? Because I had to erase. What? Contraction. So the claim is that this is same as that. So let's see. The first expansion, 1, which means that I'm not going to pick anybody, so that corresponds to 0 contraction. The first time, I'm going to take a first order, and then half because this is symmetric. Okay? Symmetric. So, and then I'm going to choose any two such guy, right? Any two such guy, by scanning through everybody 1 to n, right? And then I'm going to get rid of those guys. Instead, I'm going to replace those two guys with a contraction, right? And then I'll keep going. Second order, now I have 2 pairs of this, so I'm going to choose 2 pair of this by scanning all possibility. And then I'm going to erase those guys by taking the derivative, and then replace those guys with the contractions of each, and keep doing until the end. And if you reach the maximum, meaning if the number of this derivative is more than actual this, obviously what you get 0. You keep doing the derivative until you get 0, that will saturate, and then you will hit the point where you get the maximum contractions. Okay? So that's basically the fancy way of writing. Good.
What about the factorial from the unity?
Factorials.
You emphasize that the coefficient is 1.
Yeah. Am I confused? Are you worrying about 1 over n factorial? From exponential? So let's see.
Derivatives will cancel the higher order terms. So you might have a 1 over 2.
So this 1 over 2 is literally because whenever you get like phi 1 or 2, this also give you phi 2, phi 1, which are the same. So that cancels these two.
But the higher order terms are. So the 1 over n factorial is always going to be 1.
Or 1. Are you answering his question?
Yes.
Okay. Are you convinced with his answer?
Can you say it again?
In the expansion, the higher order term of the expansion will disappear because of the derivatives, right?
Yeah.
So the higher order terms will have 1 over n factorial, and they'll be irrelevant. So the only term that's relevant is 1 over 1. We have a 1.
What do you mean by higher order?
Just in the expansion. The first order term is the only one that survives.
Okay.
About to be convinced. So have fun discussion after class, make a friend of each other, and you move on. You will have 1 over n factor to the this to the n. So there will be permutations, all of these factors. Okay, and that will be basically eating up the 1 over n factorial, but you think about it. That's basically how things go. As usual, right? Combinatorics. Okay, so that's good. So now we are equipped with this powerful theorem, Wick theorem, because now whenever I see this t, where would you see? Exactly in the context of scattering, right? So this was t, scattering t, e to the I e for x, and then interacting Hamiltonian density. Okay? So, this will be an interacting Hamiltonian. For instance, the example of interacting Hamiltonian, which I guess we're going to use quite often, can be a product of the two complex scalar with the one real scalar. Okay? So this is all defined on obviously a single space-time point, right? This on its own. But, so this is a time order, so you can expand this formal expression, 1 over minus in and factorial. And then you will have many integrals to do, e for x1, e for xn, and then you will have time ordering of all this interacting Hamiltonian circuit. So now superscript is for this space, right? So good. So this will be a sort of this is Dyson series. This is what we are going to play with in the context of perturbation theory, right? So we will have a zeroth order, which means that the leading order of the S operator is just 1, which means it doesn't do anything, right? So if you have initial particle, then it will just go to the final particle, nothing happens. Then the first order, second order, and so on and so forth. So provided that this is a small effect in the sense that the G is small, the interaction is weak enough, then we can study given scattering processes order by order in this expansion, right? That's why we want to study. Now the question is, okay, this comes with this time ordering, and is there any more useful way of representing it, re-expressing it? And that's exactly where we're going to use this. Okay, the contraction, as we talked about, is a propagator. Oh, I see. Something can be represented as a propagator. What if there's something that is uncontracted? We can think about that. Okay, so the next thing I want to discuss is that given this series, Dyson series, and Wick extension, we're going to start talking about Dyson, because Dyson's formula, and then we're going to talk about Wick expansion, which means that we're going to re-express this in terms of normal ordering product. So that's Dyson Wick expansion, and then eventually we want to develop a diagrammatic method in terms of Wick diagrams. Okay, so that will be the topic of discussion from now, for a while. Okay, so now you know this. So from the get-go, let me just mention the following. Otherwise, we may get confused. Is this the Feynman diagram? Because that looks exactly like the Feynman diagram. What's the difference between Feynman and Wick diagram? Okay? What we are going to do is that I want to develop a diagrammatic math. You think you can do it, can you? Okay. Diagrammatic method representing operators. These are operators. So the Wick diagram representation is a diagrammatic representation of operators. On the other hand, eventually we are interested in looking at a particular scattering processes, right? And fix the order in this Dyson Wick expansion. This thing has many different kind of contractions, right? As we saw, right? Single chain has many different kind of interactions, different kind of contractions. Different contractions, as you will see, can represent a different type of physical processes. So this single one can contain many different kind of physical processes. So Wick diagram is representing basically again operator, but then when we are interested in specific physical processes, which are labeled by initial momenta, so P1 to Pm, and then final momenta, so K1 to Kn. So we want to have again another diagrammatic method useful for computing this actual scattering amplitude, not the operator, scattering amplitude labeled by initial final momentum. That is the technique that we will call Feynman diagrams. Is that clear? So Wick expansion is for operators labeled by space and point. Feynman diagram is for scattering processes labeled by momenta. So Feynman diagram living in the momentum space diagrams, Wick diagram living in the Poisson space diagrams for operator, for transition amplitude. Okay? Good. So with that clarification, let's actually jump in and discuss this relationship. Okay. To discuss that, let's take a concrete example, because that's the easiest way. Well, I already have written that. So we're gonna take this as an example to discuss this correspondence between operator expansion and the diagram. And we can call this theory, roughly speaking, very roughly speaking, Yukawa theory. In real world, actually Yukawa theory, these are actually fermions, but we haven't introduced the fermion yet. So I'm just going to use complex scalar, just to mimic those things. Good. So then, if I take this as an example, let's look at a second order in this S operator. The second order in the S operator, it will include G square, so I'm literally expanding this, 2 factorial, and 2 time integral, 2 space-time integral, time ordering, and then 2 of them. So, which will be 1, 2. So far, I have written literally the part that I would expect to get. Okay? And this will have all kinds of contractions. So, what types of contractions this can possibly have? But before that, let me actually zoom in and focus on only one of the terms, actually interaction term. Okay, and talk about it. So interaction Hamiltonian in interaction picture, which is G. Okay. You know, we are now living in the iPad, so I cannot just copy paste right there. So I have to do this. And here is the starting point of a diagrammatic representation. So at a given X, somehow these 3 guys meet each other. So first I can represent as this. I will put arrows, I will explain, and whenever arrow comes out, then we'll represent the psi coming in, represent psi, daggers or psi, and then phi. So there is a convention I have chosen. So let me explain the convention I have chosen. So this arrow represents a charge fluid. Okay? In other words, charge plus 1 flew in, charge plus 1 coming out at this particular space-time point. And this is a real scalar, so it doesn't carry any U1 charges, so I don't put anything here. I'm assuming this here respects U1 symmetry for this complex. Okay? Now, why that convention and which convention exactly this corresponds to? In order to think about that, let's recall the fact that this can be represented as alpha p, like this, and then beta p dagger. Okay, so this annihilates a particle, and this creates an antiparticle. Okay? And, you know, this dagger will have obviously beta plus alpha dagger. And then phi is this A and then A dagger. Okay? With the exponential factor calculated there. So now let's ask what this diagram actually represents. What types of physical phenomena this represents. So out of this point, which it had nothing out of, if I put this as my momentum direction, okay? Then, if I use psi dagger, what it does is that it creates what? It creates what? If you look at the operator representation. It actually creates this, right? Well, that's not a correct sentence. It creates a particle. On the other hand, imagine I'm something coming out of that vortex. In this case, psi, looking at it, this actually creates antiparticle, beta. Okay? And then obviously, if I can do this way, this is now momentum flow. So I'm looking at this momentum flow. That was charge flow. This is my momentum flow. And then obviously, in this case, it creates this little particle A. So the convention I have chosen, I'm violating my rule. You know, there's a name rule because it is to be violated. If it is never violated, you don't have to call it a rule, right? You just call it a truth. So there's a rule, I'm gonna violate right now, so I'm just start using blue. So the convention is this. So if I had a charge flow, and then momentum is the same direction as charge flow, that's my convention for my diagram for particle. Hence this was indicating, okay? And then if you have a charge flow and then momentum direction reverses it, then this represents diagrammatically antiparticle. And if I chose this convention, then I know this had to be psi dagger, this had to be psi. Okay, and this is phi. You can interpret the other way around. What if I chose momentum flow going in? So there was a particle disappearing toward at point X. So then you ask which one gets annihilated. Obviously, psi dagger annihilates antiparticle. Again, consistent with the diagram. Even if I flip the direction of momentum, right? And then now, which one gets annihilated? It annihilates the particle, which is again consistent. The momentum flow is the same direction as charge flow, etc. So that's my convention. Therefore, my labeling is that something that coming out of the vertex is psi dagger, something that comes towards it is psi. And phi does not mean good because particle and antiparticle are the same. Okay. I know I'm gonna use this. Who has a creative idea?
Erase that.
Accept reality? I accept this?
Yes.
I want this to be here.
Okay.
Thank you. That was very helpful. I appreciate for your support. Okay, so now let's talk about what types of diagram this can possibly include. And then the ultimate goal is that we establish sharp, precise mathematical correspondence between these. Okay? That's our ultimate goal for today. But for now, let's just explore a little bit about this. So this one includes this. I'm gonna have to write like so many times of this like today. So this include. Let's just think about what types of things this include. Somebody has to invent. Somebody. Because I need to write this 4 times just now. Just now I have to write 4 times. No, let's just do it. 1. And actually more. 4 is enough. Let's start there. Let's look at a different contractions. So first of all, according to Wicks theorem, +1 times it should include all types of contractions. So let's look at the 1 contraction sector. Okay? So I can look at this. You can ask, what about that? For instance. Okay? So let's see. First, let's translate this in terms of diagram. So this will look like, so I have insertion of this, and this corresponds to psi dagger 1, and this is psi 1 and 5. And then coming out is psi 2 dagger, psi 2. Then contraction between phi 1 and phi 2. So that gets connected as a propagator. So this is a diagram. Okay? So let's do this. So I'm gonna have to contract this too. So this comes out by 2 coming in. This is a charge flow, and this is a diagram. What about this? So this comes in towards the first vertex, coming out second vertex. This is the diagram. What about the last one? So coming in. Oh, that was, yeah, it is. Somehow charge flow, there should be crash, right? So unless your theory include U1 charge violating operators that can rescue this thing, this will give you 0 answer, right? In a theory that doesn't have a U1 charge violation. So these are diagrammatic representations. For instance, is included in the second order in this expansion. There are more, so let's actually explore a little bit more. You can have another contraction. Can I recycle? Okay. Yes, I can recycle. So these are 3 diagrams, right? And then I can even create. Can I? Boom. Boom. So you can ask, what is this 3 contraction diagram correspond to? Okay. So that corresponds to. Right? So every 3 lines are contracted. So this corresponds to this types of a loop diagram because it has a loop in it. And in particular, this types of diagram is called either vacuum to vacuum transition or just vacuum bubble diagram. Why? And you understand it looks like a bubble, right? You understand it's a loop. You might say, why vacuum? The reason it is called a vacuum is because suppose this is your time direction, and then you look at the time, which is sufficiently earlier than the first time, and you look at the time sufficiently later than the second time. So here, nothing existed. So it is actually vacuum. And then here also nothing existed. So it is a vacuum. So whatever it happens, it describes the transition from vacuum to vacuum, but with something non-trivial happening in the middle. Okay? So that's the sense it says it is a vacuum transition diagram or vacuum bubble diagram. There's another thing that can happen. So let's look at another example. So this time, let's just take this diagram, contract a scalar only. And then ask which diagram represents this one. So basically, it is this diagram, but now scalar is not free, they're contracted. So, which means this. So this time, it contributes to a physical process of, some complex scalar state into complex scalar. So it's actually propagator, right? Yet, it makes a non-trivial loop contribution to that propagation. Okay, so initial state consists of a single particle, final state consists of a single particle, so it goes from the one particle to itself, but with non-trivial loop diagrams. Yes?
I have a question about the direction of the line segment. The left border, right border, I think the diagram indicate that the charge is flowing out from the point. But in that diagram, for example, second row, the non-contracted side to dagger, it makes the charge flowing in to the point 2.
Good. So can I then clarify now? I will answer that in a comprehensive level. That's a great question. Looks like is this like particle going to the particle, antiparticle going to the antiparticle, or what? Like you can ask that question. So is there a question related to that question? Give a single diagram. Exactly which process this corresponds to.
Indeed, my question is just very rudimentary when I mean, apparently, the apparent diagram looks opposite to the convention defined earlier.
Oh. Oh, yeah. So it should be the other way around. Is that what you're saying? Yeah.
I mean, I was curious about that.
Yeah. So because here, side one is left, so it should go in, and here it should come out. The other way. Sorry. If that okay. Okay, you're happy now? Yes. Thanks. Okay. Now, then let me give you an answer to not your question, my question. What types of physical process does this describe? Okay, so let me answer that question. So for that, let me take this example. Okay, exactly which process this diagram corresponds to. That depends on the direction of the time you take. Okay, so let me. This can represent the 4 different processes. So first of all, let me take the time direction going up. So I'm reading that way, which means that momentum going in like that and momentum coming out. That's what I mean. So initial state has what? There's a phi and phi, right? Coming out. But then coming out momentum, this one is parallel to the charge flow, so that should represent a particle. This one actually reverses the momentum direction. So it should correspond to antiparticle, which let me represent as this label. Okay? What if I take my time direction going downward? So now this time, this is particle, this is antiparticle converting into phi phi. So that should correspond to psi diagram going to phi phi. What about if I take the time to flow from left to the right? So I have a phi. Now this is reverses, this is psi dagger. So phi psi dagger going into phi psi dagger. That's great because I'm not violating charge, Q1 charge, right? Charge -1 turning into charge -1. And let me take the other way around. So now I have a phi and then particle going into phi and particle. So that corresponds to, again, I'm not violating charge. And the reason why I said this might be 0 in a theory without a charge violation, because now if you look at this, you have a phi particle turning into phi antiparticle. This diagram would violate charge by 2 units. Okay, so that's how you can interpret the physics of these diagrams. Okay, so that's nice representation. But now, one big question you want to ask is that given this gigantic algebraic formula, which is Dyson-Wick extension, what is the precise? So there's one way of thinking about the physics. So if you want to decline of using any diagrammatic method, I'm purist, no diagram. Then it's okay. Sit down, do the algebra all the time. Commutator, okay, commutator. You just do it, okay? And you will not have any friends. Or you take one hard moment understanding mapping between the algebraic chain to diagrammatic representation. So we are going to go through how we understand precise relationship between these two. And then you start adopting this nice, fancy, interesting machinery, so just representing everything in terms of diagram, and you will have many friends. Okay? So that's what I'm proposing to do, but I like purists too. Okay, but don't just talk to me. Okay. I will do one algebraic calculation once on board probably, and I don't want to do that again. Is that clear? Game plan? So I want to establish a relationship, and then we will just switch using diagrammatic calculations. Okay? Okay, so now we want to establish this thing. So eventually, I want to show that S operator is equal to this mysterious expression. Oh, am I going to be successful?
Maybe a little hard.
If I do hard, is that? Am I going to be successful? Sure. So the goal for the rest of 20 minutes, no, okay, 15 minutes. I want to show this is true, and such that you understand what this means. Okay, so that's all. Let's do it.
Professor, I have a question.
Thank you. Sure.
In Wick, license Wick extension,
Yes.
the A is word A and B can be a composite operator. Like,
Oh, you're asking whether these can be composite operators.
yeah.
In principle, yes.
If
If it is
no. I mean, the pi, dagger pi, psi, dagger psi, pi itself is composite operator, right?
this is a composite
Yeah.
operator. Okay.
So, is there some rule to block us to contract two operator?
Here,
Yeah.
you can do that. But okay, good. So in principle, you can do that, and you will have to do that. So the question is, so here I've been nicely contracting only one guy from one word and then the other guy from the other word. Why I cannot do this contraction? You can do that. So let's take the example. At the risk of not having time to prove this, let's take the example of Hamiltonian, the interacting Hamiltonian is a lambda applied to the fourth. Okay? So now you have the same guy. So suppose I look at the second order like this. So then in principle you can contract same guy from one side and then you can connect. So this may correspond to a correction to phi to phi propagator with two loops. So yes, you will have to do that. And in fact, if you recall the general formula, not this, it had a something like this: 1/2 I and J in the phi by contraction. I'm not labeling stuff, okay? And then chains. In fact, this is run from 1 to n without putting, say, inequality. I don't write this way, right? So in principle, you could have chosen the two operators from the same side, and you will include this type of contraction. That's a good question. Good. But
Apparently, that kind of contractions are infinite because you said the propagator is the momentum at the
it is infinite.
integration of delta.
Yes.
Yeah, delta e to the IP.
Yes.
But if x and y are same, then
Yeah.
obviously.
Obviously infinite. Terrible. Right? Terrible. Oh my god. We shouldn't continue our.
How can we do?
Yeah. Oh my god. Let's stop. Let's start the semester here. We just have a final exam. How about that? And I'm assuming you understand everything. Yes. So this, if you nicely compute it, you get a infinity. You need to learn a nice technique to make a friend with infinities. Okay. And it's called the renormalization, and it will happen next semester. I don't know whether it will happen with me or with other professors. Okay. So, but it will happen. So anyway, so this will nicely give you infinity. Not only that, this will give you infinity. This will give you infinity. So many different kinds of infinity, and it can be tamed out. We learn throughout history how to fight against infinities. Sometimes, I don't know. So going back to this, I had to simulate how I can get to this one. Good. There's a logic. So I can explain this in a maximally confusing way, so that you can leave the field. Or I can try to explain, hopefully in a more clear, understandable level. So let me try something in between. So S is given by, I told you I needed this thing, minus I n over n factorial, a lot of integrals. Let me not write the T4x stuff, and then this time ordering. Would you forgive me if I just drop the I, okay? You know what I mean, right? So, there are several things to understand. So point number one, wake up. Point number one. By point number three, you will be doomed. Point number one, this include by Wick's theorem. So now I'm talking about on the Wick expansion side. Okay? Remember, I'm trying to establish Wick expansion side to Wick diagram side. I'm gonna make a statement here, I'm gonna make a statement here, right? So on the Wick expansion side, this includes all possible contractions, right? So that was Wick's theorem. So now, what will be the corresponding statement in the Wick diagram side? So to do that, let's actually look at these two contractions. Erase blue. Okay, erase blue. We had this, we had that. Okay, so Wick expansion includes not only this contraction, but also it includes this contraction, obviously. Every possible contraction should appear. And then if you look at this, these two diagram is related by permuting these two vertices. Right? If you swap 1 and 2, it looks like this. So on the diagrammatic statement, which means that this includes, with a subtlety, with a very important subtlety, all possible permutations of this vertex point. Okay? I have not said where all permutations give you distinct separate diagram yet, different thing yet, but at least it can include all possible permutations. Modular subtlety, I'm going to explain that. Okay? So that's the aspect from the Wick expansion. This is aspect from the Wick diagram. However, there's a subtlety. So in this case, if you permute, you get actually separate diagram, right? This is not same as that. However, if you permute this is the same diagram. So that's the observation you can make at the level of a diagram. Let's ask which aspect of the Wick expansion side captures that. Because if you permute this, okay, on the Wick contraction side, there's only one unique contraction. Okay? So there's this humongous contraction expansion according to Wick theorem. There's one unique contraction which can be represented as two different diagrams. One this, the other two. But nicely, on the diagrammatic side, it knows that fact because it comes back to the exact same diagram. Okay? So that's observation number 2. So if there's only single unique contraction, this is related by the fact that two diagrams or many diagrams, doesn't matter. So let me just say a set of diagrams. So can I just, this is my notation for diagrams, Wick diagrams. All those diagrams which are identical under permutations. That means that if you have a diagram like this, you permute the vertices, you get the exact same diagram. That means that on the Wick contraction side, there's only one contraction appearing in the Wick expansion. Okay? Good. Okay. Anyway. So that allows us to define the notion of what's known as the symmetry factors. Okay? So there is a notion of symmetry factors. So I'm not done that list yet, but let me define a symmetry factor. So for a given diagram D, I'm going to define symmetry factor as an SD. So okay, so you see, something like this will appear now. So symmetry, what's that? A symmetry defect out there. Symmetry factor. That's in my phone. Symmetry factor is that the number of permutations that give you the same identical D. Okay, so let's take this example. So in the case of this thing, right, symmetry factor is 2, right? Because of this 2, you get the same answer. What about this? The symmetry factor is 1. Like there's no other the permutation you can get you the same diagram, right? What about yes, 1, 2, 3, 4. Basically, you can go around the chain without modifying the diagram, but obviously, if you start changing actual ordering, you get the same different diagram. So in this case, symmetry factor is 4, right? You just to go around the chain. Good. So with this preparation, now let's achieve the first step. The first step. Okay. So then, note number 3. So in order to do this, let's actually note the following fact. So I have this. N and nth order. So let me represent this as a whole bunch of different contractions. So let me just label as C1, C2, C3. You will have many, okay? CL, whatever, right? Ton of different contractions appearing. And let me define the second option. Suppose there's a class which are all related by permutations of the vertices. The sum of diagrams simply are not related by any permutation at all. So for instance, even if you do any permutation here, you will never get here, right? And then if you do any permutation here, you will never get there, for instance. So at fixed order in the expansion, for instance, if you look at the n insertion of, nobody told me. I really remember that. Really? Are you with me? Really? Okay. I doubt. No, I have to. Unfortunately, you will not gonna guess. You will understand this today. But hopefully, let's prepare the ground, okay? So that we can quickly get there. A fixed order in n. This include a lot of different kind of contractions. I'm about to explain to you that there are a set of different contractions. For instance, this, together with this, with the reverse arrow, right? They are related by the permutations, right? And then there can be another class, etc., which are all related by only permutations. So I'm going to divide this Wick contraction space according to equivalence class, which are just related by permutations of the vertices. And then I'm going to call this class, which have the same class or same pattern or same diagrammatic topology. So this thing has the same diagrammatic topology as that. This thing consists of a single element inside, because no permutation will give you different diagram. This way can get you a lot of different kind of thing. But anyway, so I will cluster everybody that looks like this in this single equivalence class, or I call it topology or pattern of the diagram. Okay? Good. Now, what I was telling you about the symmetry factor is that even if you have this, you're not gonna get n factorial different number of actual diagrams. In this case, you actually get 2 different diagrams. But sometimes you only get single diagram, even if you have 2 vertices. Right? This is for slightly different. So therefore, in each class, the number of actual distinct diagram, meaning matching to actual contraction space, is equal to n factorial number of vertices. I see angry eyes looking at me, and then symmetry factor. Okay, so that's the number of distinct diagram in this class, and then you just have a different classes. Now, therefore, this Dyson Wick expansion operator side can be written as, I'm going to sum over all different number of vertices, okay? And then this one, the claim I'm gonna make is the following. And then there's integrals. That this particular just the operator side consists of some or different patterns or topologies at nth order. So there are different kind of classes. And then I told you that there are not completely n factorial different kind of thing. But some of them get you the exactly same diagram. Whenever you get the exact same diagram, it means that there's only single associated contraction. So there's no two different kind of contraction, there's only one of them. That's what's capturing the symmetry factors. And then here you will have a particular, let me just put it as a diagram. Okay? With patterns or topology. Okay? So this is the first realization, and we will have to continue from here. Only two more steps, I think we did get there. Okay? So I'll stop here today. It's a terrible point to stop. That's life. Which means that you will get another chance to see this argument again quickly next time. So we will stop here. Next time I will show this, and then I will start discussing Feynman diagram and Feynman loops. All right, thanks.